Hello, everyone. My name is Deriu. I work at the Zurich University of Applied Sciences. And today I'm going to talk about speaker diarization and more of an applied view. This work stems from a collaboration with Spinning Bytes, which is a startup located in Winterthur. It's a spin-off from our university and ETH. And we are currently building what we call INTERSCRIBER, our product, or a Spinning Bytes product. And the idea is that we want to transcribe automatically interviews or meetings or any kinds of conversations. So for instance, if you are a journalist and you are interviewing lots of people, it takes a lot of time to transcribe these interviews manually to text and then assigning who said what when. And we want to automate this process. Also for meetings, if you have like a company with lots of meetings and you need to create the minutes, then transcription is like one thing that you might have to do. And with this, we want to make this process easier. So of course, as you might already guess, there are like a couple of components there. So you have the speech to text component that transcribes, like just takes the audio and creates a lot of text. But then you also have to find out who speaks when. And if there are more than two people, you have to also know like who to assign like which sentence to. And of course, since these like models are not perfect, the main product is also to have like an editor that allows you to make the corrections. And we can speed up the whole transcription process. I think the last number that I heard is like by 5 times. In good cases, even more. But like the average is like you're 5 times as fast with doing this. So one thing that we are, if we are talking to customers, it's like the confidentiality. And there is the problem that we don't want, or the customers don't want to have their audio sent to Google or Amazon or IBM because like they are sensitive data. They are not allowed to send them overseas or in a situation where you don't really know where the server is. So we have to provide an on-premise solution for that. For speech to text, that's not really a problem because there are solutions that you can run locally and that work quite well. However, for diarization, we weren't really satisfied with the quality out there. So in order to solve this problem of confidentiality, we have to build our own diarization engine. Okay, so the diarization engines, they have like various types of qualities. And one problem that we saw, apart from like very bad machines, but also in our case, is that they tend to split sentences. Like here, here the sentences das wie ein Kätzchen schnurren will, anstatt zu brüllen wie eine Höfe, bei so viel Harmonie muss sie das sogar ein wenig skeptisch machen. So this part here should be part of this sentence here. And if you think about it, it should be done like automatically because it's quite clear that skeptisch machen is not a sentence. And also here, wir wollen Politik gestalten, that we put this wir down here. It's quite obvious to us humans, but the way that diarization engines work, they don't include like linguistic information in there. And that's one problem that we want to tackle. I'm aware it's a bit of a cosmetic problem, but if you are in the business of making a great impression on potential customers, you have, of course, to solve these problems. And this is also one of the reasons why we had like this shared task yesterday that was organized by Don Tuckener about finding out like what is a sentence from just text without punctuation. Okay, just a bit of context about speaker diarization. Very broadly, it's just getting audio and then splitting audio into who said what when. And the diarization part is assigning pieces of audio to different speakers. There are different settings. One of the hardest setting is if you don't know in advance how many speakers there are. But in our case, we assume that we know that. So in our interface, the person specifies, the user specifies how many speakers there are. So at least we know in the clustering part how many clusters we have to build, which if you have done some clustering, you know that's quite hard to do automatically. But the idea is you get like an audio file and you want to create these segments here. And the standard pipeline looks mostly like this. And this is also, if you look at most papers, you have like the input, like your audio input, you do some feature extractions. That's mostly some MEL frequencies or creating like these spectrograms. That depends a bit. Nowadays, you just put it through your neural network in raw form, using like wave to wake 2.0, like whatever. The second one is the voice activity detection, which just looks at sections where there is actually speech, because at the end we have like this clustering step, and if you have like silence or background noise, then without anyone speaking, then it can happen that your clustering sort of merges two speakers together and you have like one cluster for the silence, which is not really what you want. So you want to remove these sections from the audio that have silence in there. Then you have to, then you take it and do speaker change detection. And speaker change detection is not just, it's like finding out when from one speaker you go to the other speaker, but it's not like you know to which speaker you go. It's just like at this point, there has been a change of speakers. And then in the next steps, you find out which speaker you assign this to. You also can do overlapped speech detection. We didn't do this, or we handle overlapped speech differently in our tool. But for the diarization, we don't look at this. So the speaker change detection gives you like these segments of speech. And then you take these and you cluster them in order to sort of assign like each of these segments to the speakers that you have. And if we look a bit at what the outputs are from the speech activity detection, you mostly get like these kinds of lines here, which is like the output from your neural network, which at each point in time gives you a sort of confidence if there is speech or if there is silence there. You can see that here is already like one problem that you have to solve is how do you interpret this kind of speech and silence? Because if you just say everything that's above a threshold of 0 or below 0.5 is silence, or if you take some other threshold, like I mean, normally you would, if you would look at this as a classification task, you would just say like everything above 0.5 is speech and everything below is silence. But as you can see here, that's not quite true. So you have to do some bit more massaging of everything and looking, okay, are there peaks or is this just an outlier or stuff like that? And there you can already lose a bit of information if you do this without much care. In this example, of course, it's super nice because like these dips here, they correspond to the gaps, but you have to be quite careful here. Also, the same thing for the speaker change detection. You get scores here with like these spikes, and you have to interpret them like how big should these spikes be in order to say, okay, this is a speaker change. And if you and here, if you do them like too lenient, then you get like an over segmentation, which is okay, but it can hamper with your clustering then. And if you do it like too strict, you miss a lot of speaker changes. And it's quite hard to calibrate because you have to do this calibration manually. And depending on your test set, you come out with different values, and they don't necessarily then translate to your use case. So it's quite a tricky thing. So I will explain how we handle this later. And same thing with the speech overlap detection. Okay, let's quickly look at the clustering. Because for clustering, you also take the raw audio as input, you process it. So you take like windows of like 1 second, 4 seconds. It depends a bit on your algorithm. And then you encode them using an LSTM, for example. You can also use any other kind of neural network. And but in this case, the LSTM returns a hidden vector, which is called the D vectors. Other kinds of networks give you other names of vectors, depending on the authors of the papers. But these vectors are then used to sort of represent the audio or the fingerprint or the speech print of the voice. And based on these embeddings, the clustering is then applied. And the clustering, you can take any algorithm that works best. You can take spectral clustering, which works nicely for nonlinear data or data that is not linearly separable. So that's mostly the clustering algorithm that is used. But essentially, you will assign each of these vectors, which corresponds to 1 second of audio, to one of the clusters. And if you say we have like 2 speakers, then you will create 2 clusters, and each vector is assigned to one of them. Okay, so this is what happens if you apply the standard pipeline, like I showed you before. It seems quite okay, but you see that there is a lot of over segmentation, like segments where the same speaker is speaking and the speaker change has been predicted. It can be, of course, that if someone makes a small pause during the speech, that this is noted as, okay, this is some speaker change, but it doesn't really represent like the change of voice. And you see also that there are 3 speakers. You have like the narrator, and then you have the interview here. But in the clustering sort of didn't work well because the narrator has been sort of split into like into A and B, and person C has been put here. So this sort of is a sign that the clustering, like the embeddings, are not really good, and also maybe like the way that these segments have been created sort of hampers also with the clusterings. So like these are the problems again, like the speaker change detection. If you do it too leniently, you get like an over segmentation, which can cause problems, especially if the segments are too small. Then it's quite hard to create a good embedding from there. And if it's too strict, you get like you miss out a lot of segments or changes. And also for the clustering, most pipelines that are openly available are trained only on like one like standard corpus, which are meetings about some product design, and that's not enough. And mostly are just built for English, but we want to also handle German language. So we changed the pipeline a little bit because we have a bit more information there. So we do voice activity detection. As I said, this is crucial. And then we just segment the audio into 1 second steps with a bit of overlap. And we used like these 1 second segments as clustering. And for us, that works quite well. And then we also have like the speech to text engine. And the cool thing about that is that the speech to text engines return a list of words, and each word comes with a start and end timestamp. And we can exploit these to sort of change the task into assigning words to the speakers instead of just doing the clustering as before. So this makes the whole thing a bit easier. And then the speaker change detection, we apply it for these kind of scenarios, as I showed in the beginning, where we are not sure if there is a change, like an end of sentence. If we go back here, because if you think about it, like one or two words, they are like just as a fraction of a second. And if we do like the splitting with 1 second segments, then of course it can happen that the second that we do the splitting starts here instead of where it should be here. And then we can use like the speaker change detection as one kind of signal in order to say, okay, here should be that change, and it's more precise than like these 1 second splits. And then we have like this assignment. If we have then assigned the words, we can see, we can look like, is this a sentence? We can see we can ask, is this part here a sentence? Or would it make sense to add this word and this word? And then if it says, okay, probably the sentence goes from here until here, because we have to add another 2 words in order that it makes sense. And this is quite easy. We did this very naively because the speech-to-text engine that we use actually provides us with punctuation. So we can just use like a standard sentence splitter like Spacey that returns sentences. And with these 3 kinds of information, like with the clustering information, with the speaker change detection, and with the sentence, how should I call it, sentence checker, we can like sort of fine tune this very well, and it works. It works quite well for our case. We used as our test set a corpus that we created ourselves because we wanted to recreate the scenarios that are relevant for our use case with interviews, and especially with audio with very bad quality, because if we want to have users that just put the phone on the table, record the interview, and then just upload this, we cannot expect them to have like a professional setting of perfect interviews. It should handle very bad audio. So we have a test set where we have these scenarios in there. It contains 16 audio files in German languages, various lengths, various topics. It's 1.5 hours of speech. And as I said, the quality in audio is a bit more varied. Now let's look at the error rates. We have here the rate, the diarization error rates, which just looks at how many seconds or milliseconds have been wrongly clustered. So the oracle, if we have an oracle that tells us exactly where the splits, where the speaker changes happens, we get an error rate of 17%. And here are like the clean, average, and challenge. They are like the various like difficulties of the audio files. So as you can see, the clean ones with very nice audio data has like a very low diarization error rate, whereas the challenge with very bad quality and people talking over each other has like a very high diarization error rate. As you can see, the traditional pipeline that I showed before has like double the word error rate, the diarization error rate. And yeah, that we cannot really use that. So that's why we had to rearrange things a bit. If we do just the 1 second segmentation pipeline, that is without these changes like the speaker change detection and the sentence thing, and also without the speech to text part, we get like an error rate of 23. Especially here in the clean data, we have a bit of problems. But with the complete pipeline, we get a very good word error rate of 20.1. And also comparing to the commercial systems, like from the big names, which I censored here because I wasn't sure if I should make these things public. We have like a better diarization error rate on our data set, which is and on German data than they have. So that worked also quite well. So one thing that is quite interesting to note is that if we do the ablation with the is sentence thing, we don't get a change really in the error rate. And that is because the changes that are made at this level, they are so fine-grained that they don't really are measured, since like you also allow in the calculation of the error rates a bit of a leeway, saying that yeah, if it's like 100 milliseconds or 250 milliseconds to the left or to the right, then it's okay. And so then you won't really measure these kinds of things. So we can look at an example here. The reference has like, again, we have the narrator and then we have the interview here. The traditional pipeline, as I showed before, makes like all these kinds of errors. But our diarization sort of almost perfectly aligns with these, with the reference. Of course, there are still errors that we cannot handle if there are like interjections, some very fast like back and forth, then we cannot really change, we cannot really detect those simply because they are too short to embed correctly. So we lose them, and then that's the human editor that has to correct them. All right, then a bit of outlook. We might have to do a human evaluation to see if people, if there is a difference in adding these parts to the pipeline. And the human evaluation is mostly, you can just look at how many corrections they have to make with and without that, which is quite easy to integrate. Then also, if you think about the application of speaker change detection or diarization, you can also create a speaker recognition around this. Just like if you have like a registered speaker there, it already recognizes the speaker, and it's then easier also to do the clustering. If you have older data from a speaker that you already know, you can use that also to refine the clustering. Then we can also apply like newer technologies like Wave-to-Vec 2.0 to create better models. Like in the last 6 months, there has been like a huge push in many of these speech recognition, speech processing applications just by these new things. And then we can also see if we can train jointly speech to text and the diarization thing, if that sort of helps improve the quality. All right, thanks you very much for your attention, and I'm open for questions now.
Thank you very much, Jan. Are there any questions? Jan, I didn't get it, how you calculate the average of your diarization error rates.
The average, okay, it's
that there is a weight or something.
Yes, it's weighted by the number of minutes
okay.
in the 3 columns. Yeah, so it's a weighted average.
Maybe I have a short question about the window size. So that you use for segmentation.
Mm-hmm.
I think this really sort of determines or limits the granularity at which you are able to detect speaker switches. So
yes.
How do you deal with that? And you said in evaluation you give some leeway, and I think this is because you want to not punish the model if it's a bit off in this regard, but maybe you can say something about the window size.
Yeah, so the window size, it comes from it stems from the clustering algorithm that you use, because the clustering algorithm expects like 1 second audio. So that's just the natural way of doing that. Because if you think about it, if you have like less and less audio, then your clustering creates embeddings that encode less and less information. And that's also, as you said, that's the main problem, that you lose the granularity, because 1 second is a lot in terms of words. You can say like 3 to 4 words in 1 second, depending on the language. And that's the reason why we do the rest here, like the speaker change detection, to make it finer grained. Also the sentence thing with more from the, like the linguistic side, and the whole speech to text thing. So like all these kinds of things here are just to correct like this problem here. Then the leeway, regarding the leeway in the evaluation, that's just the standard way that diarization error rates are computed. And I use the standard scripts to make everything like coherent. I get why it's done like this. I mean, if you have like your reference, then it's not perfect. And people also make errors when annotating. And these, like, not errors of 2 seconds, but errors of like a couple of milliseconds. And that's why they add like this, what they call color around like the reference point, so that they can sort of handle also reference errors. Yeah.
Okay, thank you.
Thanks.
Maybe I have also a short question. Yeah.
Yep. Sure.
Thank you very much for your presentation. However, it's not exactly my field, but I had a question. Maybe it's a bit general. I want to know how that, since this task was kind of include of several subtasks, I want to know how did you deal with error aggregation? I mean, like,
yes.
you have a speech to text and then sentence. So how did you deal with this error aggregation during each task?
Yes. Yeah, thanks for the question. Yeah, essentially, if you think about the work that we did, is like exactly that, handle error aggregation. So we pushed out the speaker change detection from our pipeline to make it not a liability up here, so that the errors from the speaker change detection are, so that the role of the speaker change detection is a corrective one and not one that makes errors itself. Also, the speech to text thing makes errors, but it's so good at the moment that it's more corrective than destructive. So from that point of view, it's okay. And also the voice activity detection has more benefits than it destroys things, because even if it's not perfect with finding the silences, like in the millimeter, at least it removes so much silence that you will never end up in a situation where you accidentally create a cluster that is composed of just background noise. So most of these things do more good than they do bad. So the hardest culprit, like the speaker change detection, we just pushed it out, and that's mostly what we did to do like these error aggregation problem things. And then doing like 1 second overlaps, that there's no errors there. So
okay, I see.
Yeah,
thank you.
Thanks for the question.
No problem.
Okay, thank you very much, Jan, for your talk.